So, let's have a look at the contest results so far.
The question is, can your stream even handle
Can my stream handle what?
1080p?
It's a presentation at this
Could your
point.
network even handle? Yeah.
I
Could your
mean,
network even handle 1080p?
this is 720p stream, so it's fine.
Oh. Okay.
I haven't gotten Discord. Wait, do I have 1080p stream?
I mean, it's.
No.
I mean, you can only 1080p stream to friends.
Yeah.
So like anyone who's you're not friends with has got to like just keep it 720p at this point. Yeah.
All right. So I'm assuming these are Gordon, Arsalan, Kevin, Andy, Lily, and Eston. Am I incorrect? Doesn't look like it. Okay. So and we have Rayton, who's on his attempts. Rayton, if you're here, you're really close. You just have to fix one thing. And I already gave you that hint. So that's going to be that's how our contests are going. Remember, this contest is going to be up until next Wednesday, in which after I think I'll take down the problems. I might just keep them open after, like, for not the contest, but like for you guys to see, and like submit them for the rest of the year and stuff like that. But let's have a look at another concept that we're going to be doing today. Quick mic test. Can you hear me?
Yes.
Clear? Like, clearly?
Yes,
Yeah.
very
Yes.
well.
Yes.
All right.
Magnificent.
That's good. Okay. So, we're going to learn something about called coin change. If you have already done problem 2, then you've already somewhat made a way to solve a general coin change problem. And if you have done so, I want you to go and work on, where is the problem? This one. I want you to go work on this problem right over here and put that in senior. Work on this problem, and then if you've done that, try to go ahead and start this problem. This 12-point problem is a bit harder. I know the idea now, but I haven't implemented it yet. A coin problem requires a little bit more thinking. Am I echoing from someone?
Yeah, Yang.
Yeah.
Wait, but how? Because I have a mic. I have like headphones in. So
Yo, Sat, we did golf in like junior comp sci.
Okay, then go ahead and try doing a coin problem. You're gonna.
I did that one.
You did?
Bash your what? You already did? Dang.
I think isn't that just a coin? It's just I might not.
You probably haven't done it yet.
I can check.
Oh wait,
your
this is the
submission.
12-point one, right?
Yeah.
Yeah.
No, I don't think I've done.
Okay. So go ahead and give that one a try, and if you manage to finish that, then you can either work on any other dynamic program problems or sit there and have fun.
I was joking.
Don't sleep. Sleeping is for the nighttime. Okay. So, if I had correct grammar, I would know that this is. Okay. So let's pretend that there's this random kid we know named Shangbo. I don't know who would be named Shangbo. But let's just pretend that there's a Shangbo that we know, okay? So Shangbo is in a situation where he has n different types of coins, with the ith coin being worth DI dollars. Since he has only money from, I really can't type, chores, Shangbo wants to spend at most V dollars at the store, but wants to maximize the number of coins he uses. What is the amount of money he spends, and how many coins does he use up in the process?
Your stream is dying.
Okay, let me just turn off my
Yeah.
video.
He's dead.
Can you guys hear me still?
Yeah. Now you're.
All right. Do you guys
Better.
mind if I don't have video on?
Yeah, it doesn't matter.
All right.
Doesn't really take much away from it.
All right. So, I'll repeat it. He's in a situation where he has n different types of coins, with the ith coin being worth DI dollars. Since he only has money from chores, Shangbo wants to spend at most V dollars at the store, but wants to maximize the number of coins that he uses. What is the amount of money that he spends, and how many coins does he use up in the process? Solve this problem in two different ways. Number one, he has an infinite number of each coin inputted, and number two, he has one of each coin. He only has one. He doesn't have infinite numbers. He only has one of each coin that's inputted. Okay, so let's have a look at this. So let's do this first problem. He has an infinite coin. He has an infinite number of each coin inputted. So if you've done problem 2, then you know that you've done a problem where it tells you to minimize the number of coins he uses. So okay, yeah. So you have to minimize. So what's your strategy if he has an infinite number of each coin inputted? What's the strategy for maximizing the number of coins each time? Anyone want to give it a try? Okay, if not, then we'll just go straight to the replit. Alright, I'm assuming people can see my empty program. Okay.
Yeah. Yes.
Alright, so our goal is to, given an array of n integers representing the types of coins, we have to maximize the number of coins being used. So, you might have been, last time you would have done something like you'd have your DP array, or the array that you'd use the amount to compute at each step. Alright. So you have a total of DP array with a size of V. And then at each step, this would hold this holds a minimum amount with a sum of, let's say, that index. And so originally what the good approach is to originally set the DP array to really huge numbers, because you optimally want those numbers to change and like become realistic values. Because since we're doing a minimum, since we're looking for the minimum at each step, it's best to set the value to some really high number, so that if you reach that really high number, you know that at every point, that for any coin value that you have, you're never going to reach that number that high, so that the DP originally will take that value. Does anyone have any questions about the approach, of setting to really huge numbers? Okay, it looks like we're good. And then also, with a total of $0, we have, you know that DP of 0 equals 0, because there's no charge to make, make or to use no money. No number of items is required. That's the better way to put it. Okay, so knowing this, now that is if we had looking for min number of coins. Now let's try doing looking for max number of coins, because obviously that's what the problem I proposed was. We have to maximize the number of coins being used to make a value p. So this time, what isn't going to change is the fact that dp0 will still be 0. Because it doesn't change that no number of items will make a use of $0. So we still have to use that, but this time, since we're looking for the maximum number of coins, we want to fill the rest of the DP array with really small numbers, impossibly small to reach. Because then, when you go ahead and put in the new coin values for the first time at each index, that value will always be the maximum. And maybe no one said, but I should probably make it clear. Let's say we have DP, we're looking for a DP of I, and if we set that to a really low value, let's say -5, you know you're never going to reach -5 with anything. And then your operation would be something like setting DP of I to be DP at I minus the weight or the value of the coin plus 1. This value is always going to be higher than the starting value of -5. So that's why we want to fill our DP array with really small numbers if we're looking for the maximum number of coins. And similarly, we filled our DP array with really large numbers if we were looking for the minimum number of coins, because they were impossible to reach or impossible to be not beaten. Okay, so let's look at our specific values. So we have n is number of coins. Let's restrict n to be between 1 and 100. And then the value of coin, let's restrict that to be less. All coins are less than or equal to v in total value, and then our total value that we want to spend. And let's say that 1 is less than or equal to v is greater than or equal to 1 and less than or equal to 10,000 or 1,000. And our objective is find the maximum number of coins used to reach a total value of v. And then, of course, there's the case of you cannot reach a value of v because, let's say if you have coins are like 2, 4, and 6, and v was equal to like 11. You know that you can't make 2, 4, and 6. You can't make that. You can't make any permutation or different ways to add them up to be 11 because those are even numbers. So if v equals 11, which is this is a case where v can't be approached, not preached. Approach output -1. So that's going to be what our objective is for this problem. What do you guys think? Do you think I should take this up right now, or should I give you a few minutes to think about it? And remember, if you've already done problem 2 from the contest, then I feel like you're good to go for the 2 problems I gave you, or any other problems, because this is just about the exact opposite thing as of compared to what we're going to be doing here. Okay, I'll give you guys until 4 o'clock to briefly think about it, and then we're going to go ahead and take it up. Okay. Actually, I'll keep myself unmuted. I'll just copy these restrictions. Alright, so go ahead and think about that for a few minutes. Actually, I'll give you until 4:05. And this is the approach. So try coding this yourself, actually, because I gave you most the main idea of the approach, and then we'll go ahead and take it up. So you'll have until 4:05. I'll just... This is what we're looking at. Okay. I think that was enough time for you guys to have even the slightest idea of what the problem is like. Can people confirm that they can still hear me?
Yes.
All right. It's actually not great with the virtual environment because I remember people like Adam and Anish, who were my teachers personally, they would always walk around while people were taking their time solving questions. So I can't tell exactly how far you guys gotten because I can't just look over your shoulder and see, he or she is getting this, has gotten this far in the problem. So it's hard for me to get an idea of where you guys are at. With that being said, I'll just go ahead and get started with the solution. Okay. So, we have our int n, v, and those are going to be the values of the number of coins and the value that we want to spend. And then our value of a coin, di. So let's just store all the coins in the coin array. Int coins 101. I typically make it 1 bigger than the actual size just so there's no weird behavior. So int coins 101 because there's at most 100 coins. Remember, some compilers have problems with non-constant sizes, so I can't do something like int coins n when I get input for n. So, but Replit will be fine with it, but it's better form to have a constant size. So int nv and then int coins 101. So let's take our input. Actually, first, before we do that, we always want to use fast input because it can't hurt you. So, because actually, someone remind me, what is the difference? What effect does using sim.sync with stdio and sim.tie 0 have on the output and the way it's done? It's faster, yes, but anyone have an idea?
Mess up the format. Like there's that question that we did like 2 years ago.
That was, yes, I remember.
was,
That
like,
was
really-
that was the
Yeah.
Python fast input version. C++ doesn't have any problems with that.
Okay, sorry. Whoops.
But that's a good answer.
It desyncs from C input and output.
Yes, it
So
desyncs. So what effect does it have for people who don't have that terminology? Like, what does it do?
Okay, so naturally with C++, okay, so it will await with C++ input and output. It will wait for C input and output, and so when you desync it, it pretty much just like unties from each other. It doesn't have to wait for each other. So
Yeah, so it takes in all the input and then does all the output. So in some sort of interactive problem, you never want to use sim.sync with stdio and sim.tie, both 0, meaning false, but rather just not using it. But in those interactive problems, I don't see the input sizes being really huge. Otherwise, you can use different ways of input and output, namely scanf and printf. But never use both scanf, printf, and cout in the same thing, especially when you have a desyncing output or desyncing input command, because then, as Gordon has ran into very recently, it will mess things up. Anyway, let's get in our input. So cn n. Wish I could type. Alright, so now we have to take in all of our coins. So for int I equals 0, I is less than n, I plus plus, we have to input our coin, cn coins of I. And then we have to take in our total value for v. So our first part of the question is an infinite number of each coin inputted. So we have to go ahead and give that a shot. So now, ultimately, we want to just create our. We want to create a table with a bunch of, as I've said here, we want to create like a DP table or a DP array with a bunch of really small values, such that you have the highest amount of coins no matter what you do as your first action. And then our maximum value of V out here was 1,000. So it will be good enough to keep it inside the int main because it's not going to hold it in the stack. So now let's take our let's create our DP array, but this is essentially going to be the maximum number of coins. So int DP, and the maximum size for V is 1,000, so I'll go 1001. Because I'm going to need all indexes or indices from 0 to 1,000 inclusive. Okay, and let's go ahead and fill our array. So we can use the mem set that we did before, but because these are negative values and the mem set stuff is really weird to me, honestly, unless we're doing mem set value as 0, I'm just going to go ahead and use a for loop. So at first I know that dp0 has to be equal to 0 because we declared that for no items included, you can only have a total value 0. Or actually, that's reverse. If you want to spend $0, then you're always going to have 0 items. Because I'm assuming the values of the coins are always at least 1. So let's go ahead and take in for int I equals 1, I is less than or equal to, and then we have to go up to 1,000, but realistically, it's up to V, where the maximum value of V was 1,000. So for int I equals 1, I is less than or equal to V, I plus plus, dp of I equals some I'm going to make it equal to some negative number because I know it will never be approaching that in real life. So dp of I equals -1. And also a funky thing about the way it chose -1 was that where V can't be approached, you have to output -1. And so if I set it to -1, then I don't have to do any casework at the end. I can just print dp at V because I know if it couldn't have been reached, then I had to output -1, and the entire dp array was filled with -1s, so it would have worked out nicely. So we're going to fill our dp array with negative values of -1. All right, now we have to go ahead and do our coins. So now we have to go through each of the indexes from 1 to V again. And now we have to do our casework and assign dp of I to be max number of coins to have total value of I. So we're going to go ahead and do that. Now I recognize that you could have also just combined these two for loops because you set your dp of I equals -1 before accessing dp of I, but this just makes it more clear in the lesson, so I'm just going to do it as is. A total value of I. Not impossibly, but just I. Alright. So for every spot, we have to check if we can for every index or spot I, we have to check the following. We have to check the following for every coin. One, can we even add the coin onto a value to reach I? Namely saying, is I minus coin value greater than or equal to 0? Because if it's less than 0, then you know at that value of I, you cannot even put on the coin value because it's going to exceed the value of I, so there's no point even trying. And number 2, is it more optimal to add the coin coin count from I minus coin value, and you have to add that add it with 1 because you're going up using 1 coin. Or you just, is that more optimal, or do you just keep the total that's there already? So that's the two things that we have to check, and if it's more optimal, then we obviously want to change it. So now we have to go through all of our coins. So I'm going to have this is going to be a nested for loop for int j equals, and I did 0 indexing of my coins, and j equals 0, j is less than n, j plus plus. Now we have to work with the first step. Can we even add on a coin and get to the current index I? So if I minus coins of j is greater than or equal to 0, and if so, we just see if it's more optimal. So this can either be done by an if statement, or we can just use the max function in C++, which is built in for those who don't know. So we can just set DPI to be the maximum of the original value of DPI, or the old value per se, and then we have to go back to I minus the coin's value, and the coin value is coin of j plus 1. And remember, this is because you're going back and you're taking your total value from before, like the maximum number of coins from before, and you're adding on 1 only because it took you 1 coin to get from I minus coins of j to I, because you added on the total the value of the coin itself, which was coins of j. So dpi equals max of dp of I, comma dp of I minus coins of j plus 1. And now simply, as I said before, if dp of I was, if the total value was possible to reach, it should be updated. Otherwise, it will have a value -1, which we want to output. So now we can just go ahead and do our last our final print statement. Cout dp of v, because that's the maximum number of coins we want to have. And I don't have a specific test case, so we can just create one ourselves. Let's say we have 5 coins with values 2, 3, 4, and 6, and 8. And we want to reach a value of 63. And since we're asking for the maximum number of coins, if we had to do this without really using a computer, we know that we want to use the value with the minimum number of coins. So if you use this 30 times, you can get the value of 60. And if you use this once, you can get a value of a total value of 63, because 2 times 30 plus 3 equals 63. And so this would be 31. And because we use the lowest value every time, this is actually impossible to beat. However, it isn't, in some cases, it's not as fast to implement a greedy solution like this. So that's what the greedy solution is in our head. So we want to input 5, then 2, 3, 4, 6, and 8, and then our value is 63. And here we have our 31. So this is our, therefore there are 31 of the maximum number of coins to get a value of 63, assuming that an infinite amount of each coin is 31. So that's going to be our final answer for this part of the question. Does anyone have any question with how I approach this? Can I at least confirm that people can still hear me?
Yes.
Yep.
All right, good. So I'll definitely be posting this in the server. So if you were too shy to ask, or you realize that you have a question later on, you can always refer back to the the code. But now we want to look at the second part of this question, which is has only one of each coin that is inputted. So knowing that of what we've done before, if there's only one type of each coin, what is this? What are we essentially solving here? What concept have we gone through that is essentially the same as this? Anyone want to give it a shot? Well, that's
Isn't
okay.
it kind of like, oh, sorry.
Oh, go ahead. Go
Can
ahead.
I have? It kind of reminds me of knapsack.
You're correct. We use knapsack in minimum, using minimum number of coins, minimum number of coins. So instead, we're just doing a knapsack with a maximum number of coins. That's essentially what this is. And you're you're correct. Part 2 of problem uses knapsack. And the approach, I'm not going to go through it because we've taken up a knapsack problem before. But essentially, instead of doing knapsack of I of j equals knapsack equals minimum of knapsack of I minus 1 j comma knapsack of I minus value of coin. Oh no, I minus 1 j minus value of coin. Plus 1. Instead of doing that, we're the intended solution is just the opposite. Let me just write this. The opposite is knapsack I of j equals the maximum of knapsack of I minus 1 comma j and I minus 1 comma j minus value of coin plus 1. And as done before, or as attempted to do before and I posted the code, you can shorten this down to 2 arrays because you're only relating knapsack of I with knapsack of I minus 1. So you can relate 2 arrays and therefore greatly decrease memory in the long run. So that's going to be part 2 of this problem. And I'll leave that for you guys to go ahead and try to code. I'm probably going to post a problem with that later on. I'm not sure exactly when, but I'll try to add it on to our collections of problems that are due Wednesday. So that's going to be our, that's going to wrap up our coin change. So coin change and knapsack, as you've seen, go kind of hand in hand. Where instead of just using one value, you're using at most one of each coin. It can be like use unlimited of each coin. So it's very familiar to knapsack. So yeah, go ahead and try using 2 1D arrays. So I'll give you these two. I've given these 2 problems that are really good to go ahead and try: a coin problem and CCC 2000 S4. A coin problem is quite difficult because you have to think of some way to optimize it, but it shouldn't be impossible to think of. Curious, anyone here that finished the problem? Like, has anyone actually done a coin problem before and gotten an AC on it?
Close. I am close.
I tried it with Python and it just said no. So
No, it's okay. You have to make it very efficient. That's the problem.
Yeah.
So-
If you want, I can give you guys hints on it. I haven't really implemented the problem myself, but
I can give you guys a hint. What
I know
think should
what
AC.
the approach is after thinking about it for a night. Okay, so that's gonna wrap up coin change, and really that's all the. I think that's all the dynamic programming topics I'm gonna go through, because in the end, most dynamic programming problems are really just, if you're in Junior Complex Club, you're familiar with stuff like prefix sum array and those kind of methods. But really, dynamic programming really is the best way to approach dynamic programming is try writing the values stuff out on paper, and then seeing, hey, is there a way I can relate my current value with previous values? If you can do that, then that'll be your probably your best solution, as it'll be under the dynamic programming category. But sometimes they are really hard to think of or really hard to prove. So that's why dynamic programming problems start really simple, but these familiar concepts that you have now, they can go on to be really, really, really difficult to implement. Like there are 40 and 50 point problems just on dynamic programming. But yeah, I feel like that's all I'm going to go through. I might go through some very advanced topics later on, but that's probably not going to be done until after CCC. So now, most people would think that I would go ahead and go straight to graph theory. However, I'm going to take a 1 week, I'm going to take this time that we have left to introduce a concept that has appeared a couple times. Now, it's called hashing. So, let's have a look at what it is. Hashing is a very interesting concept that has many applications. The idea of hashing is that it maps an object to a certain value or number, which is easier to access and manipulate than the object itself. If you guys don't understand too much of what I mean, then just keep listening, and I'll give examples as to how it works. But if you've done grade 12 computer science, you know Java has a hashing a hash function built in, but sometimes you've had to override the hash function and make your own. And so in comparative programming, using the idea of hashing, it can make space or time complexity or both much better in certain problems. As I said before, you might think it's kind of goofy to learn about after learning about dynamic programming for the now 4 weeks, but it's proven to be really important in recent contests. Even though it's banned from the, even though the concept of hashing is banned from the IOI syllabus, I feel like it's something that you guys still should know because it's going to have a lot of applications if you choose to go into computer science in general. So let's have a look at hashing. Files, hashing.cpp. If I could spell, that'd be nice. Hashing. Okay. I'm just going to write the template code. So we define hashing. I don't know why I didn't indent. Hashing is you take some sort of object and you assign it a numerical value. And there are different ways to do hashing. But we're going to learn about one for now because it's the most common one. On some object. We are going to learn about the rolling hash, which uses a polynomial function. Now, if you're Kevin Zhang or anyone that understands the rolling hash, you're probably bored for another hour again. So I highly encourage you to go ahead and try some hashing problems if you haven't done so already. I'll link them right now, actually. But I know, Kevin, you've probably done all these problems, so you can go ahead and try some other cool problems. I was making a list, but
Kevin's not here.
Oh, great. Has anyone? Actually, there are definitely some people that have done hashing.
Only S3.
Yes, that is the main. That's the main thing that angers me. 20S3. Okay, so we're gonna learn about the rolling hash. So, in CC, if you don't know about CCD 20S3, it used the idea of actually used the idea of rolling hash, and it used strings. Where the optimal solution was to use hashing occurring with strings, which is going to be the most common thing you use the rolling hash on in dynamic competitive programming. So let's have a look at how it works. So you want to imagine having strings of really huge length, like 10 to the power 5, even 10 to the power 6, and you want to see if they're equal, like multiple times. So the normal string 1 equals string 2, it'll run in O of n time, where n is the string length, because it has to check each individual character and see if they match. But hashing allows you to pre-process a string in big O of n, and after do comparisons with other strings in a much faster time. It's actually big O of 1. So if we found a faster way to do this, we can compare really fast, and this is known as a rolling hash. So let's have a look at our... so the rolling hash uses a polynomial, let's say p of x, where you relate it to a series of coefficients a0, a1, a2, a3, to some value a of n, and then a value of x. So a0 times x to the power of 0, which is just a0, a1 times x to the power of plus a1 times x to the power of 1, which is a1 times x, plus a2 times x squared, plus a3 times x cubed, plus, and then this continues on to an x to the power of n. So this looks really intimidating, I would imagine, to some people, but let's decompose it. So p of x is our rolling hash function, and it has a degree of, not degree n, it has supposed to degree of n. It has degree n, and it has n plus 1 terms, where you have something with a coefficient x is 0 all the way to something that has coefficient of x to the power of n. So there's n minus 0 plus 1, which is n plus 1 terms in the polynomial. And this x value is going to be the constant value. And then you have these coefficients a0, a1, a2, to an, which can be different. So that's a polynomial. So how can we use this for a string? Or, yeah, let's just take, for example, a string, because that's what the rolling hash is mainly used for. So if we let our... now we have to think about first... so we have p of x equals a0 plus a1 x plus a2 x squared plus a3 x cubed plus plus a of n x to the power of n. So obviously we know that so p of x is a rolling hash value, x is a given constant, and a0, a1, and then to a of n is our coefficients that change. So obviously, in the string, we want each character of a string to have the values a0, a1, a2. We want to map the characters in the string to the coefficients of the a coefficients, because those are the things that obviously change. But how can we relate the characters of a string to numbers? You guys probably learned about this in ICS 3U. So someone give me an answer. How can we relate the characters in a string to numbers?
Code.
Thank you. Let's be more specific. Huh?
Convert a char to integer.
Yes. What's the method we use to do that?
You can just call int. You can just typecast it.
I know, but int. What is that called?
Parse?
Parse?
No.
Parsing.
It is the blank value. I don't know who said that. Yes. Whoever said ASCII first is correct. We're going to use ASCII.
You ASCII.
Well, that's essentially what converting to int does. So, as a reminder, ASCII is... so the ASCII value for A is 65, or capital A is 65, I have to emphasize that. ASCII value of B is 66. ASCII value of C is... Well, I should keep it all capitals. 67. And ... And then Z would be assigned to 90, I believe. Yeah. So, in many coding languages, they have the ASCII thing, have the thing called ASCII values, such that the characters are mapped to certain values, or certain integer values. And in lowercase, lowercase a is 90, a is 97, lowercase b is 98, lowercase c is 99, and so on and so forth. And then lowercase z is 122. So that's what. So now we have a way to relate characters to numbers to use in our polynomial. So now, so let's assume we are working with only lowercase characters. Now we'd have, if we convert our a to an integer, let's actually go ahead and do that. This is simply just going to be a typecasting. So if you have like char character equals c, and then we were asked to find the ASCII value, in C++ you can do cout typecasting int of the character, and if we go ahead and run that, it would give us a value of nice. Apparently doesn't work in function main. What did I do wrong? Multiple definitions of main. Let me move this over to a new REPL. Sorry about that. Hashing intro. Yeah, I don't care about that. Refresh my page. Okay, so if we were to print out the ASCII value, can be done by just typecasting the int to a character, the int of the character we're looking for, and we see that the ASCII value is 99, and that was the same as what we had here. And these general conventions can be found by just searching up ASCII value table or something like that. But let's keep working on it. And this is ASCII operation, or ASCII operation, or ASCII converting, or whatever. I'll just leave ASCII operation. So first of all, so now we have an idea of what the coefficients of a0, a1, a2, dot dot dot. So a of I is going to be related to ASCII values of each character in the string. So now we have to find a way to use these ASCII values in a way that this will work for a value p of x. So that means that we can take in a string input, and if we want to find the rolling hash, now we just have to assign a value of x, like a value of x to use in the rolling hash. And this one we're going to have to really think about how we're going to approach this. But before that, we see, if we look over here, a starts at 9. If we're looking only with lowercase characters, a is 97, b is 98, dot dot dot. So that means each for b is 1 greater than a, c is 1 greater than b, dot dot dot. So essentially z is 25 greater than a. So instead of working with numbers 97, 98, 99, dot dot dot, not 999, that's a bit big, 122, which are really big, we can simplify that to 0, 1, 2, 3, dot dot dot, 25. And how did I come up with those numbers? I took ASCII value of character minus 97. So that means instead of having a assigned to be, instead of the old values that I'm going to use, that I was going to use, or that's shown here, old values, we're going to assign new values. They're smaller and easier to work with. A is being 0, B being 1, C being 2, and dot 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 dot, and with Z being 25. So we're going to reassign the values, and the coolest way to do this, I believe, in C++, and this works in Java too, if we want to get a better version of assigning characters, we can actually do cout. If we want to find the better version of C, and we know it's 2, but how we get that, we take C minus A. Now let me explain myself, because people might be lost. When you have a minus operator in strings, or in with characters, these values will be default converted to integers, because the compiler knows, hey, instead of I can't necessarily subtract characters, but I can convert them to their ASCII values and then subtract them. So if we were to do 99 minus 97, it would produce a value of 2. And we're going to see that over here, I believe, unless I made a mistake. Yeah, and that's our value of 2. So to get our new ASCII values, we simply just do character minus A. Does everyone understand up until? Does anyone not understand or is unclear up until there? And the reason, okay, and I hope everyone's clear. And let me remind you, the reason I do this is because if I just keep them as 97, 98, 99, then the polynomial p of x is going to get way, way, way bigger than if we just had the value 0, 1, 2, if we had the value 0, 1, 2, 3, dot, 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 because these coefficients are much smaller. Now let's repeat our polynomial. So that's how I'm going to assign the characters. So that means coefficients of AI is ASCII value, or value of character minus A. And now we want to use, let's find a good X value to use. So knowing that there's 26 letters in the 26 letters in the alphabet, and we saw over here that A, we're going to associate A with 0, B with 1, and C being 2, dot, 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 and Z being 25. Now I'm going to I'm going to propose a statement, choose X that is greater than 25. Now, why do I say X being greater than 25? Let's say we have two characters. If there are two, let's go through this. If there's two characters in the string, let's say AB, and we chose X to be something like, let's see, 15, or let's go even smaller. Let's go 10. If we chose X to be something like 10, then the hash value would be P of 10 for AB would be, and using our using the fact that A is associated with 0, we're going to have 0 plus 10 times 15. Not 15. 10 times, I don't know what I was thinking. 10 times 2, which is 20. Because, wait, why am I saying 2? This should be 1. And I can't type. 10 times 1, which is 10. So that means our hash value in this case, if X was equal to 10, for the string AB would be 0 plus 10 times 1, 10 being the coefficient of X, and then X the value is, 10 being the value of X, where we have A1 times X, and then A1 would be the version of B that we chose in the ASCII, minus the character A because we want to reduce it. And we saw that value over here is B equals 1. So 0 plus 10 times 1 is 10. So that means our hash value for the string AB is 10. But what if we did a hash value? We chose to find the hash value of k. I had to think about that for a second because this is going to show something here. So p of 10 for string k, and now we know that this is just going to be equal to our value of a naught, and k is the 11th letter of the alphabet, so it would have a value of 10. Now we see over here, if we have 10 and 10 over here, and these clearly are not the same string at all. So we've actually ran into something called a hash collision, which means that two objects which are not the same have the same hash value. And this is because our x equals 10, our x being assigned to 10, was way too small to permit the and allows the collision. If x was something much bigger, then there wouldn't be a collision between a, b, and k. However, we have to think about now. Let's go back to once again to seeing why do I want to choose x is greater than 25. This is because these characters, the values of a naught, a1, a2, ... they're all greater than or equal to 0, and at the same time they're all less than or equal to 25. So if you found a way to make it so that our x value was, if our x value is less than 25, then that means that our a naught our values of a, a1, a2, blah blah blah, they can be greater than our x values potentially if you use the characters that are higher in value, greater than or equal to our value of x, and that would cause collision problems because if the a naughts, if the values of a are going faster than the values of x, then you're going to have some collisions. But if the value of x is something like 37, which is greater than 25, then we know that the x values will grow much faster than the values of a naught, a1, a2, ... comma a of n, and as a result will prevent collision. This is actually, hold on, this will be better to represent if I drew it out. Paint. Okay, so we have our values of, can people still hear me?
Yeah.
Okay.
Yeah. Yes.
If we have our values of a of I on this number line from 0 to 25, and then we'd had our values of 0 to some value x of x values, or x values since there's only one value of x. If you chose our x value to be greater than 25, like for example 37, then our first value of a naught is always going to be greater than is always going to be less than 25. So let's say something over here. And then our for next character, it's going to be somewhere. It can be any. Let's choose another spot for. So we have 25 plus, and let's have our next character be not 25. That'll be something like 6. So if our first value of a naught, our value of a naught was 6, and now we have our values for x is 37, and we sum some random character 15, let's say. You cannot make this value so high enough so that it's even possible to collide with this value of 37 times 15. Obviously, because it won't reach as high, because the maximum value it can reach is 25, and you cannot make 6, or in general, you cannot make a naught a1. Actually no. You cannot make the value of a of I be greater than or equal to a of I plus 1 times x. Because if the x value is really big, then that means that, and even if, let's say that a of I is the maximum value, which is 25, which means the character is dead, as long as this character it has a value of greater than or equal to 1, then if we have 1 times 37, that will exceed this 25. And it is possible for the character value to be 0, but if it was 0, then that wouldn't be part of the polynomial, and in this case that would be true. But the next character which works, a of k times x to the power of let's increase our a of k times x to the power of k, the next valid one that works that's greater than or equal to 0, this value of x to the k is going to completely obliterate this a of I value, which will prevent any intersection. Because if you have a naught is less than or equal to a1 times x less than or equal to a2 times x squared for all values, up until n, assuming, well, except for values such that a of I equals 0, then that means that that means that the previous one will never grow as fast or grow faster than the one above it, which means that it will always make the hash value larger, meaning the value of the hash value for this character is always going to be larger than this character. So you're never going to find a way to create a duplicate. Is that not clear to anyone? See, I know for a fact that I didn't explain it well because I just know for a fact that this isn't the best explanation as to why these won't collide. But if you don't understand, then I guess you should take my word for it, and I'll try to give you a better explanation later on as to why the hash or x value of greater than 25 will always result in no collision. But yeah. So hopefully you understand that one will always grow. That the next value of our x term will be growing faster than the previous character, no matter how high a of 1 is, because our x value is greater than. Actually, never mind. I know how to. There's a better way to actually describe this. A of I plus 1 times x to the power of I plus 1. Compare that to a of I times x to the power of I. And we're going to assume all a values are not equal to, and these a values are not equal to 0. A of I, comma, and a plus 1 are not equal to 0. So we're trying to prove that this will grow slower than this. So because we're trying to find some sort of comparison, we know that since our x value we're going to choose is obviously going to be positive, we can just divide both sides of the comparison by x to the power of I plus 1. Divide that by x to the power of I plus 1. And that means this will cancel out with this, and this will cancel out with this, remaining an x here. So that means a, you're trying to do this, this is effectively the same thing as comparing a of I plus 1. Oh no, I made a mistake. Divide both sides by x to the power of I. Because this would cancel out with this, and this would cancel out with this with the remaining value of x over here. So now you're comparing a of I plus 1 times x with a of I. And in this comparison, if x is something greater than 25, then that means that x is always going to be greater than a of I, which means unless a of I plus 1 equals 0, x times a of I plus 1 will also be always greater than a of I. And since that means that each term going up will always be growing faster than the previous term, which means that you're never going to have any collisions because you're never going to have collisions with different length of characters, because something with a higher character value will always grow faster. So that's my best explanation that I think I can do. I hope that's a little better as to why we want to have x greater than all values of the maximum value of a of I, namely, and our maximum value of a of I is 25. So that means that we want to make our x value greater than 25. So yeah, that's going to be why x is greater than 25. I hope you guys understand that, but if not, you can always approach me later on that one. So we've concluded that we want to choose a value of x which is greater than 25. And I will also make another statement. We want our x value in the function to be a prime. And this allows this is done to keep. Actually, no, I won't propose this right now because we have to propose something. We know for a fact that something has to change first. If our string length was a 10,000 or something like that, we know that our value of p of x can get really, really, really high. So high that p of x would exceed our maximum value that c plus of maximum integer or long or unsigned long or maximum, how do I say this, numerical value that c++ can hold if we just use the naive method. We just use this naive method with x is greater than 25. Now our solution for this is make p of x, when we generate p of x, we want to do it modulo a huge number. And what this means is we want to do this means that when we're calculating p of x, we want to do something like a naught mod some mod number times a1 times x mod this modulus times a2 times x squared modulus our mod value plus plus a of n times x to the power of n modulus modulus our value. And by doing this, we're going to make each of our values much smaller than they are realistically, but as a result, we're going to make sure that we don't exceed the maximum value of C++'s numerical, like that highest value it can take, which in C++ is stored in an unsigned long. Or most of you will be familiar with long actually, which I think will pass for most hashing questions. And the reason it's a problem to exceed is because once you exceed, you're going to go into the negatives, and then that's going to cause a lot of problems with the coefficients being positive, and then it'll loop around to, then that means your values can loop around all the way from 0 to the highest value, and then all the way to the lowest value, and then work your way up back to the highest value. It can get really messy. So by taking the modulus on each step, we're preventing any overflow, and that therefore we want to make p of x modulus a really huge number. And however, introducing a mod value can cause hashing collisions again. because let's say we did a modulo some number like 2. If we found p of x to be 1 in one case and then 3 in one case, well, you have to take your value modulus the mod value, which would be 2. So that means that you'd have an intersection because 3 mod 2 equals 1. So that means that you the value that p of x generating being 1 and being 3 would result in an actual hash collision, even though their values were different before taking the modulus. As a result, we want to have the mod value really huge and also a prime number. And the reason I say, so the really huge should make sense to you guys because the higher you go, the less times you're going to have to take modulus and the less messy you'll get. And by making it a prime number, we won't have issues such that one number is divisible by the mod and another number is divisible by the mod, or not divisible, is a factor of the mod, and you get really messy values, especially with even numbers for sure, because it will not work out well, and you'll get a lot more collisions if you choose a really huge number that's also even. It might pass in some cases, but you're going to have a less probable hash collision if you choose a really huge and a prime number, because it has less factors and it's odd, and all the properties of odd numbers that make it such that it'll just have less hash collisions. So we want to make it really huge and a prime number, and so a suitable value for mod is 10 to the 9 plus 7, which is a prime number if you guys aren't aware of it. It was actually in one of the questions, and this is a very common prime number to use that comparative programming questions use. Take it modulo 10 to the power 9 plus 7. But yeah, 10 to the 9 plus 7 will be valid, but you can also use values up until the highest value of the unsigned long, or the highest value of the long, depending on what you use. So so you want to make your mod value really huge and also a prime number so that you minimize collisions. So now our final thing that we wanted to so we said x is greater than 25, and by a similar logic, x being a prime number will be better to use, will be better than a composite number, because it can also contribute to having a hash collision, for example, and we don't want that, so we want to have x as a prime number. So typically, if you choose a prime number greater than 25 but not too huge such that it makes the program really slow, then you should be fine. Like x equals 31 or 37 or 43 or 41, 43, anywhere I'd say less than like 70 or something should work for you, are suitable options. So those are the proposals I'm going to make. Does anyone have any questions with those? Can people hear me?
Yep.
Yes.
Okay. I really hope you guys understand. I'll emphasize this again. If you have a question, please ask. If you're lost, please ask, because this is really important. Otherwise, you won't understand how the ruling hash works at all. Okay. I'll hope that you guys understand. So we have our proposals, x being greater than 25. We want to take a modulo huge number, and we also want to have our p of x being taken modulo a number as mentioned down there. And so now with all the conditions, if we have p of x that's going to be our final answer is actually going to be taking all those together and taking a modulo that huge number again, just in case there was some overflow. And with all that, p of x will be the hash value, the rolling hash value for an input string. This is actually better if I put p of x comma string. Yeah, because you're inputting a value of x and also a string for an input string. Remember, with a naught being a1 dot 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 being the ASCII values minus a, because then you're gonna reduce them to 0 and 25. So let's go ahead and actually now the task is, let's try to implement the rolling hash. So given a string str, take input, output, actually let's put some constraints. We'll put some constraints output. Output the hash, the rolling hash value. And let's have some constraints. 0 is less than or equal to length of string is less than or equal to. Now we want to make this really big so that your program won't fail on us. Let's make it 10,000. Yeah, 10,000. Yeah. So 0 is less than, the length of string is going to be, actually, no, not 0. Let's make it 1. The length of string is going to be at least 1, but at most 10,000. So, I'm debating on whether I should end this now and take this up next week, or giving you guys time right now and then try to cram it in before 5:30. Gordon, can you make a poll in the polls and everyone answers it?
What do you want the poll to say?
Would you rather have the whole week to work on this problem and I take it up next week, or would you rather have time to work on it right now and I take it up at like 5:15 or 5:20? Senior polls. Okay. So guys, head over to senior polls and answer what would you rather do. Do you want the whole week to do this question? And I highly encourage you to be honest. Okay, so it looks like a fair bit of you want to have the whole week to work on this question. So I won't necessarily work on a solution. Well, I have a solution already, but I won't put up a solution until next week. But for those that get the solution, I want you guys to go ahead and try the problems. Problems. So these 4 problems over here, I'll actually post. Senior resources. Actually, yeah, let's put senior resources. So I'm actually gonna put this here. Go ahead. Try to implement a rolling hash for week 3, for next week. If you manage to do so and want to test your solution, try these problems. So just want to make sure that this is the best problem to use. Yeah. So especially the first. Okay, so your homework for this week is going to be trying to do those 4 problems I put in senior resources, and if you manage to you have to try to implement a rolling hash, and if you can, if you're able to do so, try to prove your correctness in your solution by attempting all the problems I put up there, mainly CCC 03S4. Because that's going to be the one that has the best, that's closely related with the hashing. And I'm think BF4, the third problem, which I actually got wrong back when I did this first. Yeah. If you're able to do that, then you know what? Let me change the order. Oh, that's not good. Yeah, do the problems in the order that you see them in, because those are going to be your best practices for seeing if you get your rolling hash correct. And if not, if you always have problems, if anyone has problems, you can contact me or post in senior help. I answered some concerns for the past few days. And yeah, I feel like we should end it off here because I don't want to get into something new. Because obviously we won't have time. And also I want you guys to just work on this and try to get it. Because if you are able to understand this, then I feel like you're going to be set for a lot of problems, and this is honestly one of the concepts that I think is useful in real life.